Hi, my name is Leonardo Frid, and in this video I'll be giving you an introduction to the full version of the Caribou Cumulative Effects software. This is the third in a series of 4 videos. In the first video we looked at concepts behind the Caribou Cumulative Effects model. In the second video I guided you through downloading and installing the software. In this video I'll be giving you an introduction to the full version of the software, and then the next and final video I'll be guiding you through using a simplified version of the Caribou Cumulative Effects software. Now I'm going to begin where we left off in the previous video. And in that video we had downloaded and installed the software, and I showed you how to create a couple of shortcuts for the Caribou Cumulative Effects software. So I'm just going to move them over here so you can see them. One of the shortcuts we called the CCE shortcut, which is the shortcut to the full version of the software. The other one we called the CCE Lite shortcut, which is a shortcut to the simplified version of the software. So in this video we're going to be working with the full version, so I'm going to double click on the CCE shortcut. And so what we see when we open the Caribou Cumulative Effects software, on the left is a window that we call the Scenario Manager. And below that is an icon that says Caribou Cumulative Effects Model, and this is the sample data set which we downloaded in the previous tutorial. So if I float over it, you can see that there's a full path to the file, and the file has an extension which is SSIM or SSIM, which is the type of file that is used with the Caribou Cumulative Effects model. Now if I open up the node beside the icon for the library, underneath that there's a node that represents a project. It's called the CCE Demonstration Project. And if I open up that node, we see a series of 3 folders. And I've created these folders to organize my model scenarios. Now if you recall from the first video, a scenario is really a collection of model inputs that represents assumptions about what the future might be like in our simulation. And so in this case, I've created 3 folders to organize my scenarios according to the kinds of inputs that are being used. So the first folder, and if you recall also, the Caribou Cumulative Effects model combines 3 separate models: a caribou movement model, a body condition model, and a population model. So the first folder contains scenarios that are represented by inputs to the caribou movement model. The second folder contains scenarios that use outputs from the caribou movement model to project the body condition of an individual caribou cow and her calf. And the third folder contains scenarios that use outputs from the body condition model to project caribou populations over time. Now what I'm going to do in this tutorial is I'm going to guide you through creating a new set of scenarios, and in that way show you the kinds of inputs that are used for those scenarios, how to run the different kinds of models that we have in the Caribou Cumulative Effects software, and how to view the model results. So what I'm going to do first is I'm going to click on the little plus sign beside the Movement Model Scenario folder, and this shows me that this folder contains a single scenario that we've called Movement Model, No Additional Development. And so what this scenario represents is, at some point in the future, the movement of an individual caribou across a landscape that has the same amount of development that is currently present. So it uses the current development footprint, assumes that there will be no additional development in the future, and projects the movement of a caribou through that landscape. And what I'm going to do is I'm going to make a copy of the scenario. So I right-click on it and select Copy, and then I right-click on the folder and select Paste. But in this case, I would like this scenario to represent a future landscape where we do have additional industrial development. So I'm going to I'm just going to right-click on it and select Open. And so this opens a window that we call the Scenario Editor. And the first tab is where we have some information such as the name, the author, and a description of that scenario. So rather than this being a model of movement across a landscape that has no additional developments, I'm going to rename this to be a simulation of movement across a landscape with an additional 10 industrial developments. and I will modify the description of the scenario to also reflect that. Now in the scenario editor window, you'll see that we have a series of tabs, one called movement, one called energy protein, and one called population, and those tabs are where we organize the different inputs for the different submodels of the Caribou Cumulative Effects model. So the first tab is where we organize the inputs for the Caribou movement model. And when I point to that tab, you'll see on the left we have a tree, and the first node in that tree is the run control node. So this is where we define some information about the timing of the simulation. We are going to project the movement of a caribou through a landscape at some point in the future, starting on Julian Day 1, which is January 1st, for a period of 1 year. So this might be a landscape that's 5 or 10 years down the road. And we specify the calving peak Julian day because that is usually when the caribou aggregate most closely on the calving grounds. And so that information is needed when we project the movement patterns of caribou into the future. And we simulate this model more than once. So the reason we do that is because, as you'll see shortly, we will be using as inputs past movements of caribou to project where caribou might be in the future. But because there is uncertainty about exactly where caribou might be, we simulate the model many times so we get a range of possible outcomes that reflect that uncertainty about the locations of caribou on this landscape. So the next node in the tree you see is called Spatial Files, and this is where we bring in the maps that are required to be able to run the caribou movement model. So I'm going to point to that node, and you see here we have a list of files which are loaded into the library. And the first of these files is called the collar data CSV file, which is a file that specifies the spatial location of caribou movement in the past for actual individual caribou that have been either radio collared or satellite collared. And so I'm going to show you what that map looks like. Now I'm opening up a GIS program called QGIS. It's available for free. You could also be viewing these files in ArcGIS or any other GIS software. And what you see here in the background is, whoops, sorry about that. I didn't mean to zoom into that particular area. What you see here in the background is mostly the Northwest Territories and Nunavut in our base map. And this black outline polygon represents the approximate range of the Bathurst caribou herd, which is the caribou herd that we're using for this example video. Now I mentioned that one of the first inputs that we need spatially is past data on caribou movement. So I'm going to open up this folder on the left, and you'll see that, for example, here is radio collar data for the movement of an individual caribou over the period of 1 year. And here's an example for a second caribou over that same time period and a third caribou over that same time period. And so you can see, though, even though there are similarities in those movement patterns, there's also differences in the exact location where these different caribou moved across the landscape. And in fact, we use data for many caribou in the simulation, so this is the actual full data set, and you can see that the extent over which caribou move across this landscape occurs over a very large and potentially variable area when you look at different caribou. So that's the collar data. Just going to turn those off and come back to the software. So the second spatial input we call our development status shapefile input, and that's another map. And that map is based on the current for the scenario that we're running. We're using a map of the current footprint of development. So I can click on this footprint here, and so here we see both the extent of roads. We also see some large areas of development. Down here is the community of Yellowknife. We see some, I believe these are mines up here, these larger polygons. And we also see some dots scattered throughout, so these might be mineral exploration camps, for example. So rather than use the direct footprint of development as an input, what we do is we use another map, which is that footprint, but buffered out. And this really represents what we call the zone of influence of development. And what we mean by that is that caribou will not only modify their behavior when they are exactly where the development is occurring, but even when they're nearby, they can either sense it visually or using other sensory cues that there's something different about that aspect of the landscape, and they will modify their behavior. They may become more vigilant and spend more energy on activities such as walking and running rather than on foraging. And so that's what we call the zone of influence, and that's the map that is being loaded into the model library. Now you could either load a zone of influence map like the one I'm showing you, or you could load just the footprint and then in the software specify the extent to which you want that footprint to impact caribou behavior. So in this case, we're actually loading the zone of influence map. Now the roads are also important, and so that's what this line shapefile is. When we're modeling, simulating the addition of new developments to the landscape, we specify the locations of permanent roads, like the one shown here. And that's because as we simulate the development patterns, we need to connect additional developments to the existing road network, either directly to these permanent roads or by connecting them to existing developments that are already connected to this permanent road network. Now, the fourth input we call the vegetation type raster. And so that map looks like this. And the legend is shown here on the left. So you can see across the study area in green, we have forested vegetation types. In brown, we have taiga vegetation types. In beige, we have tundra vegetation types. And in blue, we have either barren or water. And so as we simulate the movement of a caribou across this landscape, the kind of vegetation which will be available for that caribou to eat will vary according to the vegetation type of its location. That's the vegetation type raster. We also, as an input, use a climate zone shapefile map. And so that map looks like this here. And so you can see for this Bathurst caribou range, where you've defined 2 polygons to represent different climate zones. We have in red the taiga climate zone, and in blue the tundra climate zone. So depending on the time of year and the location, which climate zone a caribou is located, it might experience different kinds of climate. For example, different snow depths on the same day according to the climate zone. So that's a climate zone shapefile. And finally, the last one I'm going to show you, we call the harvest zone shapefile. And that one looks like this. So this represents areas that are easily accessible either because of permanent roads or the proximity of communities which expose caribou to additional risk of being hunted. Those are the spatial inputs for the movement model. Now I'm going to show you how we specify the creation of new developments across the landscape. So the scenario that we copied, which was called no additional developments, just assume the following inputs. So first of all, the zone of influence. So how far outside the boundary of that development shapefile that we loaded do we want caribou to change their behavior? And so in this instance, we're specifying 0 because, as I showed you in the map, we're already loading a shapefile that is buffered out to include that zone of influence. But if we were loading just the footprint here, we would specify a distance beyond which that footprint would impact caribou behavior. Now, we do specify a 4-kilometer zone of influence around roads, and that's because when we add new development to the landscape in the simulation, those new developments will be connected to either the permanent road or to existing development network using lines, and so we need to buffer out those lines by a certain extent to show where within that line the caribou might influence their behavior. We also specify harvest zones, so in addition to those areas that are easily accessible through harvest, we also specify from developments and roads how easily it is to access caribou for harvest, and we're specifying a 5-kilometer harvest zone buffer around developments and roads. And rather than in the previous scenario, which we copied, we simulated no new developments, but in this scenario we're going to simulate an additional 10 developments. Now we don't know exactly where those developments are going to occur in the future, so we need to define some rules about the sizes, potential sizes of those developments and where they might occur on the landscape. So I'm going to say that those developments are going to range in size anywhere from a 10-kilometer radius to a 15-kilometer radius. And I'm going to specify how likely those developments are to occur in specific locations relative to where there already are existing developments. So new developments are most likely to occur nearby existing developments and roads. They're easier to access, and they're also potentially areas where they have more industrial development potential, perhaps near to existing mineral deposits, for example. So I'm going to say that they're most likely to happen within 5 kilometers of existing developments and roads, and then very unlikely to happen beyond 10 kilometers of existing developments and roads. And I'm going to say that they're about only 10% as likely to occur beyond 5 kilometers, and only 1% as likely to occur beyond 10 kilometers of existing developments. So we've defined all of the inputs required now to be able to run this scenario representing caribou movement sometime in the future in a landscape that has the current industrial development plus an additional 10 new industrial developments. So now to simulate the model, when it's ready to go, I highlight it here, and at the top we have a toolbar or under the scenario menu that says run, and I can click on that and then specify to run the movement model. Now this movement model for 20 new iterations can take about an hour or so to run. So what I'm going to do is I'm actually going to pause the recording and I'm going to return once the simulation is complete. So once the simulation is completed, you'll see here on the left that my scenario now has a green triangle specifying that there's results available for the scenario, and there'll also be a checkbox that says that those results are available for viewing. Now there's different ways to view the output of the caribou movement model simulation. Now one of the ways is if you look down here at the bottom of the scenario manager, we've got 3 tabs, one called charts, one called maps, one called export. I'm going to go to the export tab, and I'm going to double click on the location report. And this is going to export the output of the caribou movement simulation to an Excel file. And I'm just going to take the default location. And you'll notice now Excel is flashing down on my toolbar here, so I'm going to click on that. And so what we have is we have a record for each caribou simulated on each day of where it was with respect to the vegetation type, the climate zone, and the development status. So if I filter for an individual caribou, let's say caribou number 1 in the simulation, you'll notice that we ran the simulation for 1 year, so we have 365 records for that caribou. And if I filter for development status equals true, that represents the caribou being within the zone of influence of development. I'm going to click on that. So you'll see that we've got on 56 out of the 365 days that we simulated this individual caribou, it was within the zone of influence of industrial development. So that's one example of the outputs of the movement model. I'm going to close that file. Another way pardon me, we can look at the outputs of the movement model is directly in the interface. We can see a map, and in this instance it's going to show the movement of that individual caribou with respect to the zone of influence. And what I'm going to do also is I'm going to add the previous scenario where we did no additional developments. So I'm going to add that to results. So we can compare the two of those alongside each other. Now this is for caribou number 1 or iteration number 1. And you'll notice that the black dots represent the daily movement of individual caribou. So again, there's some uncertainty about exactly where those caribou are going to go, and you can see that depending on which scenario we ran, we had different locations for those individual caribou. We also see that at the top, the scenario representing additional developments, we can see new developments and new roads being added to the landscape. Now I'm going to scroll through a couple of those projections for different movement patterns so that you'll see both the locations of the black dots changing, and in the top pane you'll see the locations of potential future industrial developments changing as well. And the reason they're changing is because we don't know exactly where those are going to be, so we simulate potential patterns based on past caribou movement patterns and based on the rules that we specified for where we expect to see new industrial developments and roughly what size we expect them to be. Okay, so here's a couple of more movement patterns. So that's an example of the development output. Now, the next thing I'm going to show you is how we take these outputs from the movement model and use them in the caribou body condition model. And so now I'm going to, on the left, I'm going to close this map, and I'm going to also remove these from the results. And what I'm going to show you now is we're going to take a body condition model scenario, and we're going to make a copy of it. And we're going to modify it now to represent a scenario in which we're simulating the body condition of a caribou cow or calf through a landscape which has those additional developments at some point in the future. So the first thing I'm going to do is I'm going to remove this dependency on the output of the movement model scenario that had no additional developments. And I'll show you a little bit more about that in a second. So I'm going to double click on this copy of the body condition model scenario, and I'm going to rename it. So we're going to just call it additional development rather than no additional development. And rather than no additional developments, we have 10 additional developments. And so now what I'm going to do is I'm going to talk a little bit about the different kinds of inputs that are used for the body condition model. We also call this the energy protein model, the reason being that we're simulating the energy requirements and protein requirements of an individual caribou cow and her calf. So I'll click on that tab so we can look at the different kinds of inputs that are configured for this model. Now the first thing I'll say is that this model is quite a bit more complex than the movement model, and there are a lot of inputs that are required to define a scenario. Now we don't have time to go through all of these inputs, but I will point you to the publication which actually describes the formulation of the caribou body condition or energy protein model. This is a special issue of the journal Rangifer, and it's a publication by Bob White, Don Russell, and Colin Daniel. And you can see the URL where you can go and find this. It's freely available on the journal website, and if you just Google the title of the report and the authors, you'll be able to easily find it. So that's the description of the caribou body condition model. Now coming back, I will talk about a couple of the inputs. So again, similar to the movement model, we're going to simulate the body condition of an individual caribou cow and her calf at some point in the future as that cow and her calf move across a potential future landscape. And we start again on January 1st, and in this case we're simulating for a single year, and we're only simulating until Julian day 283, which is the time in the fall when a caribou cow during the rut is usually going to conceive her calf for the next year. And the reason we're simulating that point is because it is at that stage, given the body condition of a cow, that we can understand the likelihood that she will become pregnant again. And also, given the body condition of her calf, we can understand the likelihood that her calf is able to survive over the winter. I'll talk a little bit more about that in detail, but that essentially is how we're going to take the outputs of those body condition outputs and use them then to inform our projections of caribou populations over time. And again, because we have uncertainty about the locations of those individual caribou, and therefore uncertainty about their body condition, we're going to simulate this model more than once. We're actually going to run it 20 different times. Now, some of the other inputs that I'll briefly talk about are, for example, the snow depth, which is going to in turn influence the energy requirements of a caribou. And you can see that this is specified as changing over time and also according to climate zone. Now, you recall I showed you two different maps. So depending on where the movement model is simulating a caribou on a particular day, whether the caribou is in the taiga or tundra zone, the snow depth will vary. And you can see that on January 1st, the snow depth in the taiga is projected to be 32 centimeters, whereas in the tundra it's expected to be, or projected to be, close to 36 centimeters. Similarly, we also specify the activity budgets of individual caribou. So these are things like how much of its time a caribou is spending walking or running or foraging. And so that's important because it defines also what the energy requirements and energy inputs are for the caribou. And so I can show you a little bit more about this file if I right-click on it and say Export All. And it's going to export it to Excel. We see Excel flashing over here. And just as an example, if I filter for an individual day, you can see that the activity budget of a caribou varies according to whether it's outside of the zone of influence or inside of the zone of influence of development. And we can see that when a caribou is outside of the zone of influence of development, it spends about 46% of its time foraging, whereas when it's inside of the zone of influence or near development, it only spends 40% time foraging, less time foraging because it needs to spend more time vigilant, walking and running, because it's more stressed about the proximity of development. So that's the activity budget. And finally, the last input, or one of the last inputs I want to show you, is the forage biomass. So this one, depending on the vegetation type, whether in the barren, forest, herb, shrub, or tundra vegetation types, then we will have different amounts of plant biomass available for the caribou to be foraging on. And finally, the last input I want to show you is how we're going to take the outputs of the body condition model and use them to help us understand changes to caribou birth and death rates in the population model. And so this is a set of coefficients that's used to define the relationship between a cow's body weight and her likelihood of becoming pregnant, and a calf's body weight and its likelihood to survive over the winter. And I'll show you what those relationships look like over here. So there's a relationship between the body weight of a cow and the birth rate, or the probability that that cow will give birth. And this is what we call usually a logistic type relationship, where below a certain body weight, it's very unlikely that a female cow will give birth to a calf the following year. And above a certain body weight, it becomes very likely that that cow will give birth to a calf. And so we can see that if there's a small change to the body weight of a caribou cow, there can be quite a large decrease because of the steepness of the slope of this line in the birth rate for that cow. And similarly, there's a linear relationship between the body weight of a calf and the likelihood that it will survive or die over the winter, its mortality rate. And so a decrease in calf body weight can result in a corresponding increase in its likelihood of dying or its mortality rate. So that's what the coefficients on this set of inputs define. And so according to these, when at the end of the 283 days of the simulation, the model will use those body weight projections for a female caribou and her calf then to be able to change the birth rates and death rates in the population model. So now that we've done that, finally, how do we link the outputs of the movement model to the inputs of this body condition model? And so you see there's an input called the location, and it's currently empty. but I can take the results of the movement model run that we did with additional 10 industrial developments, and I can drag them in to this body condition model scenario. And so then this table becomes populated, and we see on each day what vegetation type, climate zone, and development status the simulated caribou is expected to be in over time. So now we're ready to run the model, and I'm going to again go to the run menu up here, and this time select to run the energy protein or body condition model for this scenario where we have additional development. Now I don't need to pause the simulation this time because this runs fairly fast, and we have the status of the simulation occurring down here on the left. Okay, and the simulation is complete. So now let's look at some of the outputs for the body condition model. So I'm going to go here on the scenario manager at the bottom to the charts tab, and I'm going to click on this chart to show me outputs for the energy protein, the body weight outputs. And so what we see in the top chart is the body weight of a caribou cow starting on January 1st, increasing over the end of the winter and the spring. And then going through some fluctuations, and this sharp decrease is when she gives birth. So, and that represents the increase in the calf weight from 0 to the birth weight of the calf. And then we see down here in the bottom chart the body weight of that calf increasing over time, up to at the end of the simulation time period on Julian day 280, 40 kilograms for the calf. And how does that compare to the simulation in which we had no additional developments? So I can right click on that, add that to the results, and so that we can see the red line now representing the simulation without additional developments, that over the simulation time period we have a projection to have a slightly heavier caribou cow, although towards the end that difference becomes negligible. It might be just slightly heavier, but really not something that's a major difference in body weight for the cow. And we see again a slight difference in the weight of the calf. Without the development, we projecting slightly heavier calves. Now recall that even small differences might make a significant difference in terms of birth rates and mortality rates for over the winter. And also recall that here we're actually showing the mean across those 20 simulations, because there's uncertainty. Each time we run the model, we get a slightly different result. So rather than showing you the mean, I'm going to show you the output for individual simulations. And so you can see that within any one simulation, there's a lot more variability, and sometimes there's no difference between the body weight of the cow at the end, and other times we see some very large differences between the body weight of a cow, depending on whether there is no additional developments, again is shown in blue, or with additional additional developments shown in blue and no additional industrial developments shown in red. And we see similar differences between the body weights of the projected body weights of the caribou calves. Just like that, you can show individual simulations, you can show the mean and the minimum and maximum across those 20 different simulations that we ran. And so you can see that there's, the tendency is that when we have no additional industrial developments in red, the maximum values tend to be higher and the minimum values tend to be lower than when we have additional developments, and those again result in small differences in the average projection across all the simulations. So those are the outputs of the body condition model. Now how do we take those body condition projections and use them to project changes in caribou populations over time? So I'm going to remove these from the results, and open up the population scenario folder. So these are scenarios that take the outputs of the body condition model and project caribou populations. And we have one scenario already defined where we have no additional development. Again, I'm going to make a copy of that. So right-click, select copy, and then right-click on the folder and select paste. And I'm going to double-click on it to open. And again, because I copied it, I don't want it to depend on the output of the body condition model with no additional development, so I'm going to remove that dependency. Okay, and I'm also going to rename it. So this one is a scenario that has additional development, but no caribou harvest. There's no hunting in the scenario. And again, with 10 additional industrial developments. Now I'm going to click on the population model tab where we configure the inputs, population model inputs for this scenario. The movement model and body condition model are simulated for just the 1 year, and they represent what conditions might be like for an individual caribou in the future when additional developments are built. The population model we run for multiple years, and we assume that those conditions will remain constant over that time period. Now this is a simplification we've made for this demonstration project. In the future, we could modify this assumption to simulate a landscape that's more dynamic in the way that development is occurring. So again, for now, we're gonna run the model starting in the year 2020, which might represent, you know, that point in time where those additional developments are added to the landscape. And we're going to assume that landscape remains relatively constant in terms of the impacts on the caribou birth rates and birth rates up to a point in time in the future, this time 2040. And we're going to simulate this time, because the population model can run more quickly, we're going to simulate a total of 50 times. Again, each time we run the model, we get a slightly different projection because there's uncertainty around those model inputs. And so by simulating it many times, we get a sense of what that uncertainty is associated with the future projections of caribou population size. And we're starting this time the model at Julian day 152, which is, if you recall, is the peak of calving, which is usually when caribou are censused. So it's most easy to compare caribou population sizes projected for these future points in time against caribou census information for current caribou populations. We need to specify the starting size for the caribou population. So we're specifying that this is a population that in 2020 is starting out at 50,000 caribou with some uncertainty around that. So anywhere between 45,000 and 55,000 animals. And we specify a standard deviation to reflect that uncertainty. And we also specify a starting sex and age structure. Now, depending on how much data you have available, you might be able to be very specific about the sex ratio and age structure of the population, or you may not have enough data to be so specific. And in this case, the bulk of the population, so 46% of the population, is starting out as females and age somewhere between 3 and 9 years of age. Now, in addition, we specify some demographic parameters. So, for example, we specify the number of offspring per female, or the birth rate typically, and we're specifying this on the birth day. This could be specified as if you're using caribou composition counts, say in the fall, then you could specify as a fall composition count date. But for this point, we're actually specifying the number of offspring per female on the birth date. And that number can vary according to the age of the female. So 3 to 8 year olds will have more offspring than 2-year-olds on average. And again, we can have some uncertainty associated with these estimates of birth rates, and those can be specified using minimum and maximum bounds and a standard deviation. Similarly, we specify mortality rates, and again, depending on how much data is available, you can specify it according to age and sex. And again, we specify an average mortality rate, but we also specify some bounds of uncertainty around those rates. And these rates can also be made to vary in time. In this case, we specify them for the beginning of the simulation, and we don't change them, although they could be varied over time if you wanted to. And finally, we specify harvest rate. So how many caribou do we expect to be hunted per year? In this case, we're specifying no harvest, so 0 caribou harvested per year. And finally, I'm just going to show you how we take the outputs of the body condition model and use them to influence the inputs for the population model scenarios. So as we did before, I'm going to take the results of my simulation that had additional developments and I'm going to drag them in. And so you can see that based on the body condition of the caribou that were simulated in the body condition model, we're expecting a decrease in fecundity by almost 4% from the average fecundity rates, and an increase in the mortality of calves. And recall that our simulations were projecting slightly smaller cows and slightly smaller calves in the future when we add development to the landscape. So now we're ready to run the population model, and I'm going to right-click on it and select Run Population. And this simulation is relatively fast to run. Okay, the simulation is complete. So now I can, in the scenario manager down here on their charts, I'm going to click on the population model chart to look at projections of population size. This is on the x-axis we have the time period, so from the year 2020 to the year 2040, and on the y-axis we have the size of the caribou population that's being projected for this scenario. So we're starting out at about 50,000 caribou and projecting an increase over this 20-year period. Now, how does that compare to the scenario where we had no additional industrial developments? So I'm going to right-click on that and add that to results, and that's the red line. And so we see that both scenarios are projecting a rate of growth in the caribou population, but that rate of growth is faster in the scenario that had no additional industrial developments. And the last thing I'm going to show you is how to add caribou harvest to the scenario. So I'm going to right-click on the scenario with additional development and select copy and paste it into the folder. And I'm going to double-click on it to open it. And rather than having no harvest, I'm going to say harvest 2,000 caribou per year. And under the population tab, if I go to the demographic parameters and I go to annual harvest, I'm going to change that absolute number from 0 to 2,000. And again, I right-click on the scenario and select Run Population. Click Yes. The simulation is complete, and you see that the green line now, we're projecting basically almost zero population growth if the harvest rate is 2,000 caribou per year. Now there's uncertainty associated with the inputs to the models, and again I can show you that if we show them the percentiles of the simulation. So this is the central 95%, or what we call the 95% Monte Carlo confidence intervals, and you can see that there's kind of a broad range, you know, there's quite a lot of overlap if we just include the additional industrial development between the two scenarios with no harvest. But if we look at the scenario with harvest, that one's clearly projecting most likely no population growth over the 20-year time period when that harvest rate is applied. Just to kind of summarize what we've looked at in this video, so I've showed you how to create different model scenarios for the Caribou Cumulative Effects model by defining inputs for the Caribou movement model, using the outputs from the Caribou movement model to be able to run the Caribou body condition model, and using the outputs for the Caribou body condition model to run movements for the population model. And we've looked at what if scenarios that incorporated varying the amount of industrial development that we expect to occur on the landscape, and also the amount of caribou harvest that occurs. Now, if you want to find out more about the Caribou movement model, you can navigate to ApexRMS.com. And if you scroll to the bottom of our homepage, there's a project called Caribou Simulation Model. You can click on the details to find out more. And also, you may want to watch the next video in which we'll be using a simplified version of the Caribou Cumulative Effects software to just look at varying caribou harvest scenarios in the future. Thanks for listening.